I'd like to welcome everyone to today's webinar, Nutrients Up Close and Personal, How Most BMPs Fail to Control Phosphorus and Nitrogen. For those of you that have not attended our sessions before, there's a chat window. Please feel free to ask your questions throughout the session. We'll try to address them during the session, or at the end we will open the floor to questions and answer session. So with that, today's speaker, for those of you that don't also know this, is John Mall. John currently directs all research and engineering activities and executive duties for Crystal Stream Technology. In addition, he holds the patents on the proprietary technology of the company. After formal training as a geologist at Florida State University and work in the state sedimentation lab, John worked in the consulting and mining industry along with pollution control and landfill industries nationwide. In 2009, John organized his fellow manufacturers into forming the SWEMA, or Stormwater Equipment Manufacturers Association. And we'll put the web address up there in a minute, stormwaterassociation.com. He's a strong advocate for better understanding of pollutant wash-off and the philosophy of design, installation, and maintenance. So with that, I'd ask that everybody join me in welcoming John. John, I'm going to turn the floor over to you.
Thank you, Jeff. Let me see if I can get this thing going correctly here. Folks, I appreciate you being here today. This presentation is, I want to get some information out about nutrients in general so that we can understand what we're dealing with here. And most BMPs today are not controlling these nutrients very well, and we're seeing more and more of these parameters like reduction of nutrients coming in as opposed to simply TSS removal. So our water quality standards today, if you look through the states and other jurisdictions that have their own MS4, their own permits, essentially we're looking at total suspended solids, which is still the dominant parameter. Also, though, today we're seeing phosphorus and nitrogen. Now, it doesn't mean that there aren't standards and TNDLs for other constituents, including phosphorus and nitrogen. It's just that many areas accept TSS, total suspended solids, as a surrogate for actually doing water quality. So other things, there's fecal coliform and hydrocarbons, dissolved metals, and there's things out there that are important. And more we're starting to see these mentioned in the protocols, such as tape and tarp and other things. So one of the problems with using something like hydrocarbons as a standard is that it's variable, it's highly variable from site to site and storm to storm. So it's very difficult to establish what a standard would be in that. So understanding that, total suspended solids, just touch on it for a minute. It's very important because sediments can impact other BMPs, obviously, and natural water bodies. And turbidity for very small sediments can affect organisms like penetration. But again, it's essentially a surrogate. Solids are important because many pollutants attach themselves to particles of all sizes. And I've got some information on that in some of our testing, which I'll share with you guys in just a little bit. But if a BMP traps sediments and particles, it's pretty obvious that the particles have to be removed at some point. It will fill up. And as those particles are removed, the pollutants are removed with them, unless in the meantime they've leached out. This is something we can see and something we can get our hands on and something we can understand. One of the problems with nutrients is that a lot of BMPs, or a lot of people, when they think of BMPs, think that somehow nutrients disappear from a BMP without any particular effort at removal, and they're taken up by plants or whatever. And part of what I want to cover today is how we fail to really work on these nutrients when we're looking at BMPs. Well, phosphorus, a lot of people don't realize phosphorus is essential to life. It's the second most prevalent mineral in your body, calcium being number one. Phosphorus is mainly contained in bones and teeth and things like that. But a lot of people will be surprised at how much of their body is actually made up of the chemical phosphorus. Phosphorus moves to the lithosphere, which is earth and soil and rocks. It moves through the biosphere through plants and animals, and it moves through the hydrosphere through the water. If you look at it, sometimes it's classed as semi-metallic. Really today it's not, as we've looked further. But if you look on the periodic table of elements, it's between silicon and sulfur. Now, right below silicon is aluminum, which is obviously metallic. Silicon is classified as semi-metallic. And if you follow down the chart to gallium, uranium, other things, you'll see that this classification is based on the availability of electrons in the outer elements and some other things that determine the nature of a element. So it has an atomic weight of 15. Right above it on the periodic table, next slide up, is nitrogen. And so these two nutrients are related in more than just one way. So phosphorus is very reactive. Generally, we don't see it as a gas at all. And generally, we don't see it standalone. There's red phosphorus and white phosphorus and other forms of phosphorus that have to do with its particular state. But it's extremely reactive, and it will combust in air. So this is unlike nitrogen, which is essentially unreactive and is a large part of our atmosphere. It's not like nitrogen can't react, but it's a lot more stable, even though it occurs in the same related column on the periodic chart. So looking at the phosphorus cycle, which is different than the nitrogen cycle, originally phosphorus has come from uplifting of rock, which weathers, and the phosphorus in our soils today is mostly coming from organic compounds that as they die, rot, and decompose, material goes back into the soil. It also comes, as I mentioned, from animals, from fecal matter. Phosphorus is a large part of any organism, a disproportionately large part, really, when you get down and look at it. But the detritus, the materials that come from plants and animals, go into the soil, and as they decompose, they become available, and some of them go in solution, go in our water. It's just part of the natural process. And some of them go back, of course, into plants. Now, phosphates in solution are precipitated, not necessarily so much through chemical means as through organic means when they're incorporated into exoskeletons and shells and bones and that sort of thing. Well, this natural cycle is interrupted in a quite dramatic way when we start adding vegetative trimmings and fertilizers, septic tanks, and discharges from wastewater treatment plants. These are the effects that are predominant in stormwater. As a natural cycle, we don't see as much leaching out of the soil, and we don't see as much as we do from stormwater because we're putting a tremendously larger amount of vegetative material into this water. Well, phosphorus in stormwater, if you look at analysis or several analyses, you'll see generally it's either described as particulate phosphorus or soluble phosphorus. Some people call it dissolved phosphorus, and in a way that's a little bit of a misnomer, but it doesn't really matter how you think about it. It's generally in two forms. Now, we use a 0.45, about a half a micron filter for a lot of things in the lab, but one of them is how we differentiate between dissolved and solid, and this is true of other particles, not just necessarily phosphorus. If it will go through that filter, even though it may just be a very small particle, we call that soluble or dissolved. So the particulate is caught on the filter, the soluble passes through. An example of soluble reactive phosphorus is orthophosphate, PO4, which you'll see that sometimes taken out of an analysis. It'll be a parameter. What was the orthophosphate as P? Particulate phosphorus remains on the filter and can be measured as a separate parameter. Essentially, it's digested, and the phosphorus that comes off is measured. So if you don't use any filtration at all, you just take the whole sample and test it for phosphorus, that's where you get total phosphorus, and you can do it either one or two ways. So the whole water sample is either measured for phosphorus or it's filtered, and then you have the soluble P that goes through the filter. You digest the particulate to get the soluble that's not so easy to react. And particles do, we think of them sometimes as small pieces of material, but it also can include bacteria and algae, coarse detritus, which is small parts of plants or the organic material which has decayed. And then you get inarticulate particulates such as clays. Sometimes phosphorus, aluminum, silicon will substitute for each other in chemical formulas. So you get smaller animals, zooplankton, that have phosphorus in their shells, or endo or exoskeletons, sediments, and then you get, of course, large plant material. So this is how we see phosphorus coming to us in order and how we kind of look at it. And there's a pretty thin line between solid and dissolved, and some particles are so small that they're actually smaller than large molecules. So we've just agreed as a standard that if it's under 0.45 microns, we're going to call it dissolved or soluble, and that was just a number that's been picked over years. And it has to do with some things, with the ability to settle, and it has to do with the ability not to clog these filters. The filters could be finer, and it's by no means an absolute standard. But removing this material requires a dissolved phosphorus. If it's truly dissolved or if it's extremely small particles, it requires a chemical process or adsorption. Now, adsorption, a lot of people don't realize, they throw the terms adsorb and absorb around as if they were interchangeable, and in a way they are, but adsorption is binding to a surface, and this happens a lot because of cations and electrostatic charges, and also because of chemical properties. But absorption is the filling of pores in a solid, like inside of a sponge. There wouldn't necessarily have to be any chemical reaction to get something inside of a sponge, and perlite is a kind of a rock, a form of a rock which is a sponge. So you fill the pores inside of a solid for absorption. And a lot of times the removal of materials is a combination of two. You know, paper towel has some adsorption and some absorption, where you're filling the pores, but there's also some binding to the material, because you can't necessarily wash a stain back out of a cloth or a paper towel. So phosphorus is very reactive, which means that most of the soluble P has already been bound to particulates when it comes to a BMP. For example, fertilizer adds phosphorus to a biomass. It is either taken up and put into grass, trees, or whatever. That can decompose, but the source of it was from a fertilizer, which is certainly soluble and able to be absorbed. And but when it gets to a BMP, it may be already taken up into a biomass at that point. So this is a copy of a test that we had done in Highlands, North Carolina, Clean Water Management Trust Fund. And if you look at what I circled, the orthophosphate as P, as phosphorus, was at the non-detectable level in this particular analysis in these particular waters. And we see that a lot. The detect level for orthophosphate and nitrogen is pretty low, but also the concentrations found in stormwater are pretty low, and the reason is this is a very reactive chemical. You will see some nitrates and nitrites out there, which are similar to that NO2, NO3, similar to PO4, and that it's a part of, can be a part of a compound. But at the same time, you see very little. The phosphate is so reactive, you see very little in nature. So this is a pretty typical analysis that we see. Now, There are some inorganic forms of phosphorus, but most of it is going to be bound up in organic materials. That's mostly plants, including algae. And soluble P that's bound to particulates is obviously going to show up on the particulate side. One of the things that makes it difficult to deal with nutrients, and phosphorus being one of them, is that it's the density of the materials it's on is very close to that of water, or it can be less than that of water. It can actually be floating. So gravity is not much help for us if we're doing a separator type device, similar to what our main product is. You're not going to be able to settle it out or necessarily float it out. It may float today, decompose, and sink tomorrow, so you could even have a changing density with the particles that are associated with it. So it's very reactive, and so we're going to find that this material is generally bound up when it gets to us. One of the questions that came to mind when we first met a standard in North Carolina that said you needed to remove 19 pounds per acre, I think at the time, of phosphorus in order to be deemed appropriate or permittable. And this was because the Neuse River carried a lot of phosphorus, and that phosphorus met in the cold water of the river, relatively cold water of the river, met the nice warm estuaries down at the Atlantic at the Cape, and there were great blooms of algae, and the algae eats oxygen, and the oxygen was not there for the fish, and the fish would die, and it was because of eutrophication or over-nutrification. This particular chart was found in a book that is done by San Anthony Falls and University Laboratory in the University of Minnesota. Let me highly recommend I recommend Dr. Minton's book. It's very scholarly, and you'd better be a pretty good chemist and at least have a pretty good background in physics to deal much, and math, to deal much with Dr. Minton's book. This book by University of Minnesota is no less scholarly, but it's on a much easier to understand level, and it's called Stormwater Treatment Assessment and Maintenance. And I thought I had yes, I do. I have a site reference to it down there, stormwaterbook.safl.unm.edu. And what they did here on this particular chart, and I have found this duplicated in other areas, it's just this one was very easy to see, was the mass of phosphorus per kilogram. And so with 1,000 grams and 2.78 grams, it's essentially, and they did the averages for me, I didn't include it here, essentially the average total is about 0.29%. So for every 100 pounds of trimming, 1% would be a pound. There's about a quarter pound, 0.25, maybe more, of phosphorus involved. So you can start to relate if you are collecting leaves and trash and other things at the curb, and your county or jurisdiction has a program. If you get some idea of what you're checking in for weight for this, you can get some idea of the phosphorus, the phosphorus that you are removing from the environment by actually removing the leaves from the yards and removing the leaves from the curb. And it can give you a good measure of how effective your program is. Also, this can be done if you're removing organics and that kind of material from a BMP. Back to our chart, you'll notice that the total phosphorus in this particular test was 0.19 milligrams per liter, in the same ballpark, 20%, 0.20% of what came through in the water. So it's a fairly comparable average. But the important thing here to notice is that our phosphorus removal, total phosphorus removal, was 74%. Now, there is no way a separator is going to get after phosphorus to that degree. If you understand that there's a lot of the soluble phosphorus that's tied up on particulates, it starts to make a little bit of sense. So obviously, here you can see if you can trap particulates, you can reduce your total phosphorus. Remember, that this soluble phosphorus is almost always going to be attached because of its reactive nature. Well, how do you physically trap particulates? It's pretty easy, really, for BMP. On the left, I have a picture of a basket where we're screening out a trash basket, we call it. Looks like it's about 9 or 10 inches deep, and leaves and pine straw and other materials that it's caught on the way in. And so these are pretty easy to screen, and we believe this process should take place on all flows. I say simple observation will show organics do not move from impervious surfaces in low flows. I was in Nashville one day and had that challenged, and almost on cue a thunderstorm came up, which was pretty violent, and all the maple leaves in the parking lot were still there when it was done. It would take this more likely to be moved by wind, or once they gather on the curve, they can actually move better. But just treating low flows for gross pollutants, trimmings, leaves, and trash is probably not a very good idea. Small particles and neutrally buoyant particles have to be filtered out. And so here on the right, you see a sand filter. A sand filter with clean sand in it can't really contribute to the adsorption when you are talking about clinging to the top, to a particle. However, this is an effective physical barrier. I mean, the leaf's not going to go through there, and it's going to be very difficult for decomposed materials to get through a sand filter. This is one of the great advantages of a sand filter. It's a physical barrier. Clean silicon sand is not going to react with anything. It's extremely non-reactive. But now you can also add a layer of leaf mulch or organics to a sand filter. And now we've got organic receptacles, and we can get back to some other processes where we are seeing organics attracting phosphorus. So particulate phosphorus is particularly easy to take out in a BMP. It's not a very difficult thing to do. If you're going to trap phosphorus, and I'm looking here on the right with this sand filter, this is the same sand filter before we serviced it. You better be prepared to have vigorous plant growth. What we've done is actually trapped all of these great nutrients on the surface of the sand. Even though we had a great over-the-top, there's sunlight available, we got a great stand of weeds and invasive plants that came in. Now, that phosphorus moved from the water to the surface of the sand and into these plants. When we removed these plants, guess what? We were removing the phosphorus. Several hundred pounds came out of this sand filter, and it was, the key word is removed. I've got the picture on the left because it was really interesting. When we were tested by the EPA on ATV tests, they said our basket was ineffective because it filled up with trash and debris. Really, they said it was a failure because it fooled their flow meters. This is really what we want to see. If I could time our cleaning to where we had a 3/4 full trash basket every time, or size the basket so it was 3/4 full, this is an excellent thing. As long as you don't have a flow meter to fool upstream, catching all the trash you can is really nice. By the way, even though I got 40% phosphorus removal in the EPA test, but 6 of the storms were conducted without my basket because they were worried about flow levels, which means probably literally a ton of nutrients went downstream during that test because it was removed. Not knocking their thing. I understand they had to have flow control, but it really wasn't a good thing for the environment. It was a good thing for getting some numbers for my device. This is an example of one of our devices, hybrid polisher, to control phosphorus. Now, I could put most anything up there, but I don't like, I really like to stick with my own stuff because I'm not picking on a particular style of BMP, like a constructive wetland or whatever. But this will show you what I'm talking about, the 2 methodologies that are important for removing phosphorus. On the left, all of my devices have a trash basket unless they're taken out by a tester that screens out gross organics and trash. We do that for a reason. We know that a lot of materials associate with these this material, especially the organics and paper. Everybody can understand. I could fill that trash basket with paper towels and have a good storm, and you would find all kinds of neat stuff on the paper towels if you analyze them. So the basket size is variable and is based on the needs of a particular site. Very difficult to predict ahead of time what's going to come off of a site. So sometimes we make them too small and they clog up and we have to fix that. That's one reason we warranty our devices. Sometimes we make them too big and they're hardly ever filled. We use a 1/4-inch mesh screen. On sites like a golf course, that's not sufficient. You need smaller mesh because of the small trimmings if you're exposed to green trimmings from a green. And on other places, the mesh has to come out because it just effectively clogs too quickly. So it's something that's a concern, obviously. In fact, we get gigged for this all the time, that, boy, we're high maintenance because you got to clean that trash out. To me, that is highly superior to letting it go downstream so you don't have to mess with it. In this particular device, on the looking on the right side, we use coconut fiber on the bottom, perlite, zeolite, and granular activated charcoal to trap soluble phosphorus. So we're using adsorption and absorption here. And I want you to know the field testing that you've seen on us is only using the coconut fiber. The coconut fiber is generally sufficient depending on what's coming off of a site. But, and on this particular illustration, we're not showing a top-down cleaning option. We have a way now that you don't have to do a confined space and remove each panel. But any BMP that you look at, whether it's a wet pond with a forebay or a constructed wetland with some sort of pre-treatment or infiltration or porous paving, you need to look at how you're going to trap that particulate phosphorus. And if you go look at the BMPs that are particularly effective at phosphorus and nitrogen, you're going to see that they involve some sort of screening and some sort of filtration in almost every case. If that's not present, you're going to find there's not much control. Let me say that this is fairly inexpensive to do and fairly easy to do. If you're going to go out to particulate phosphorus, if you have a wet BMP, floating organics and trash is not a good strategy because the materials will decompose. If the BMP is open to the surface, you're going to get invasive plants, algae blooms, and that sort of thing. And if you're underground and you've got a sump and you don't have a way of holding on to this material, it's just going to go downstream. So if you're going to trap phosphorus, you're going to have to be prepared to remove it. And that's one of the evaluations you need to make on a BMP is how easy is it to remove these types of materials. There's no magic that removes phosphorus and nutrients from a BMP. It's a chemical element. It reacts with materials around it. If you trap it, you got to take it out. Now, putting it into other plants is fine, but it doesn't remove it unless you remove those plants before they die and decompose. So if you've got a no-maintenance pond that's been out there for 10 years, whatever you've got in the pond is what you have at that moment. So you've got some phosphorus in there, obviously, if you've got plants. But the net, once it stabilizes, the net loss is exactly equal to what's coming in. You're going to be exporting phosphorus on a pretty regular basis out of that pond based on the fact that as more phosphorus comes in, you get more plants, they die, they decompose. It's pretty easy to measure the phosphorus coming out of a wet pond or any other wet facility, but it needs to be done at literally at the first flow because that's when the neutrally buoyant organics move. When you get up on a steady flow, which is the way we like to test BMPs, you're not going to see a lot of phosphorus moving because it's gone. It went early and often it will go out of the BMP. So over on the right, on the left, we are in that particular case, we are pumping and vacuuming solids out of our device to remove the phosphorus. The middle picture is a sand filter, which was working obviously very well because it had quite a stand of vegetation in it as far as catching nutrients. We removed all of that vegetation. We renewed the surface of the filter. This is an interim stage here. We've got a drainage piece down the middle. There'll be some more sand put on top, but we showed up my crews showed up and removed the phosphorus and nitrogen here. And what was growing in the plants wasn't all that we removed. We removed the top layer of sand and other places where this material was trapped. Moving along to nitrogen. Nitrogen is an important nutrient, but it is literally pervasive on the surface of the earth and in the atmosphere, and it's not unknown in soils and below the surface level. But it's not as essential for a plant. It's critical in the growth cycle, and certainly when you talk about fertilizers, there's a nitrogen component to it, which helps plants grow. So controlling in our water is important for several reasons, but most of which it is the fact that it contributes to plant growth. If you look at the nitrogen cycle, it's a little more complex, but you will notice that it involves bacteria at almost every stage. If we take atmospheric nitrogen, it's taken up by plants, and plants are eaten by animals, both of which have detritus that is decomposed in the soil. And so you might think of that as the main, one of the main functions. But we also have nitrogen-fixing bacteria that put bacteria into plants and let them get into that cycle, into the decomposing cycle. And there's nitrogen-fixing bacteria in the soil that can take nitrogen directly and change it into ammonia. The decomposers, and as a lesser contributor, are the nitrogen-fixing soil bacteria. Essentially, every stage of this process ends up at the ammonia stage or ammonium stage, at least as an interim step. And then you got the nitrification bacteria, and nitrifying bacteria take ammonia, and the hydrogen is released, and they change this through an organic process. They change this to nitrites. A nitrite is NO2. Nitrites are not exceptionally useful to plants in particular. And so nitrites by other bacteria, nitrifying bacteria, are changed to nitrates. And these nitrates they're actually denitrifying bacteria. This is a complex subject, and if you really want to get into nitrogen removal and anaerobic conditions, I would recommend Dr. Minton's book. It's a very complex process. It's not a simple, straightforward process. But when these denitrifying bacteria can actually return nitrogen gas to the atmosphere from nitrates. But most of the nitrates are assimilated up into plants. It's effective. They're effective as food there. So when we're measuring nitrates and nitrites in stormwater, they're not as common nor as ammonium as what we call TKN, which is organic nitrogen. So in this process that we're looking at, you have to understand this is a bacteria-dependent process. And the nitrogen cycle is actually pretty well known overall, and it's highly affected by the conditions in our beings. And I can refer you again to Dr. Mint for further study of what happens with aerobic and anaerobic conditions, and the importance of keeping high content of organics out of sediments that are deprived of oxygen, because it can mobilize metals and some other things. There's an interesting association between iron and phosphorus as far as how iron is reduced and phosphorus is released. So forms of nitrogen. Nitrogen is measured by measuring ammonia, TKN, total congealed nitrogen, nitrates, nitrites, and then of course all this together will make total nitrogen. And ammonia is a gas that contains nitrogen, NH4. Congealed nitrogen is a different animal. A lot of people don't understand it very well. You can think of it as the nitrogen that's contained in organic proteins. Okay, it's not like nitrites and nitrites, which are simply the right-hand radicals, negative radicals that associate with other chemicals, NO2 and NO3. So to determine total nitrogen, you got to get all these things. And TKN, I like to think of it as organic protein, organic nitrogen, or available nitrogen. It usually dominates analysis, and but when you get into looking at TKN, if you're going to analyze for it, and I've never done this myself, it's a pretty specialized process. You take your sample and you add sulfuric acid, and what you're doing is reducing this TKN down and getting your NH4, and then you have to get you have to liberate the ammonia out with sodium hydroxide, and you got to capture the ammonia, and this is done with boric acid. Now you look at the reduction of boric acid, which combines with the nitrogen. So it's called a back titration. You measure the reduction of the boric acid, and that tells you how much ammonia was in the sample. So it's kind of an interesting piece of chemistry of how they come up with that, because these are stable compounds, and so you can't. It's not easy to liberate that nitrogen. Remember, phosphorus is very highly reactive, pretty easy to liberate. Nitrogen, not so much. So looking at the nitrogen analysis here is the same chart as before. The top, inside the circle, I have ammonia and nitrogen here that was at 0.2 milligrams per liter. 1 milligram per liter would be obviously 5 times that much. But we had a 50% reduction here, but it's a very small amount when you're talking 2 milligrams per liter. Total nitrogen, on the other hand, which is the milligrams per liter evaluates out in the parts per million. And so this isn't even a whole part per million. Total nitrogen at 1.66 was reduced to 0.43 here. And that's a number that most people look at. They'll just reduce all of this to total nitrogen, 74%. But you notice right below it, the TKN was 1.36 to 0.34. In other words, it was the bulk of the total nitrogen came from TKN. And then the nitrates and nitrites were reduced by 7% here in this particular case. My ETV study said that we reduced nitrites 25%, nitrates 50%. And really that's a little bit misleading. Those numbers were so close to non-detect. They're really not. They really weren't meaningful. This is a little bit better measure, and you would think, and it's true, that we're not that good at removing what would essentially be chemical parts of compounds of nitrogen. Fortunately, there are not a ton of the total, and these compounds are generally associated with the particulates, and we get them. So if you look at, if you ever have a TKN result, total ketol or total nitrogen, they're going to pretty much track in most cases. You're not going to find a ton of ammonia or a ton of nitrates and nitrates in a sample. If you remember, the phosphorus content inside of plant materials it's variable, but nowhere near as variable as the nitrogen content. If you remember, the chart went from about 0.19 or 0.2% up to maybe 5%, but most of them were really close to the range, the 0.29%. Here, nitrogen can be as low a percentage as that, 0.25%, but it can go up to 6% or more. And overall, if you took the average content's about 2.5% of plant materials. Remember when I tell you it's highly variable. So it's about 10 times as much nitrogen as there is phosphorus in organic material, if you had to have a rough rule of thumb. In our study, looking at the total P versus the total N in that chart, we had 0.19 milligram per liter. If you multiply that times 10, it would be 1.9. Total, which I'm looking at that 10-to-1 ratio to see how close what we saw in our device was in the water to what we see in plants. Multiply that times 10 is 1.9. We have 1.66 total in. If you add in the ammonia, which was not added in, that would be 1.86, which is pretty doggone close. That may be blindfold luck, but it was one of the things I wanted to study to see how what we see in the water tracks or doesn't track what we see in plants. So if you believe that these numbers are good, and I think they're pretty good, it indicates that we were capturing predominantly particulate material. Well, we're a separator with filters and screens, and if you use your common sense, you're going to think, wow, this is mostly particulate material. So these things tend to add up. So now we know nitrogen's not as reactive as phosphorus, so it's very difficult to capture chemically or through adsorption. Activated charcoal and other materials can have an effect, but because there's so much nitrogen gas in the atmosphere, these materials captured need to be protected. They can exhaust pretty quickly. Again, with the nitrogen not being so reactive, it's not so easy to catch. So ammonia can be trapped by interaction with other materials, or ammonium, if you want to put it that way, as it's part of a compound. So physical trapping is a predominant method, just as what we saw with phosphorus. I say trapping particulate phosphorus, I could say trapping particulate nitrogen. They both are generally riding on the same materials, especially if we're talking about organic compounds and organic detritus, the result of decomposition. So the methods of trapping are the same. These are some gross pollutant removers. This is a litter trap in a river over on the left. There are also litter nets, and I haven't seen an analysis of the materials that these things catch, but I can guarantee you if there's 2,000 pounds of material in there and it's not all plastic, you're going to find very high nutrient contents here because of the physical trapping. It's not rocket science to try to trap vegetative material. The sand filter on the bottom right is brand new, and I just would love to get back to this particular filter, which is in San Antonio, as I recall. I would love to get back and get a picture of it after it's been in service for 4 or 5 years. I don't think the shrubs on the outside will be the only organic material around. And if it's maintained and the material is removed, and I'm sure it will be, then it's doing its job. So kind of summarizing a little bit here, how in the world can we be sure we're going to fail at removing nutrients? And let's thinking back to the 3 parameters. That's total suspended solids removal, phosphorus and nitrogen removal. We hear a lot about the use of chemical fertilizers, but the lack of control of physical materials is a major cause of excess nutrients entering our waterways. If we put salt water in a sand filter, we're going to get salt water out the bottom. And if we put it in my device, despite any organic material and screens, we're going to get salt water out the backside. So if we really have a lot of mobilized chemical phosphorus and nitrogen, and it is not attached to particles, and we don't have, you'd have to have a bunch of places for it to be adsorbed or absorbed. The lack of control of the gross physical materials is a major cause of excess nutrients in our waterways. Now, I'm sure these guys here in the picture on the lower right are going to take all those leaves and bag them up, but all too often this material is blown into storm drains. And when it's blown into storm drains or into the street, we see it, all of us see it every day, literally. You have to understand that for every 1,000 pounds of leaves, there's 25 pounds of nitrogen and 3 pounds of phosphorus being put into the next water body downstream. And it's the lack of physical control hitting us here. This is the sediment analysis to go a little past we understand we've got to have a physical control to get these nutrients out. This is looking at the sediment from our Clean Water Management Trust Fund study. If just looking at the numbers and going down, we'll go from the bottom up, the total phosphorus that was shown in the sediment that was removed was 935 milligrams per kilogram, almost 1%. It's 935 parts per million. But forgetting parts per million for a minute, let's just look at the raw numbers. They're all in milligrams per kilograms. We had somewhere around 3 times as much nitrogen as phosphorus, which is not reflective of what we see in plants. Now, it would make some sense that the nitrogen being more of a bulk and less reactive wouldn't bind so well to the sediments, but it's just an observation to make here that the nitrates and nitrites, again, are almost non-existent when the sediment was analyzed, so we're not keeping a lot of it down there, not capturing a lot of that. And once again, TKN here almost exactly balanced the total nitrogen in their measurement. And there's some other things up top you can look at as far as looking at the amount. We had about half as much zinc as we did phosphorus in this particular on this particular site. And where the barium number 3 down the top came from, I really can't tell you. But it's interesting to see how the sediment in a device. This isn't coming from the screen. This isn't coming from the trash basket. This is what was in the bottom of the unit in the sediment and the amount of nitrogen and phosphorus. You could go back and look at the milligrams per kilogram that we saw in the water itself, and get some idea of how effective, how much of this material is being carried in the sediments themselves, attached to particles. And you guys that have heard me very much have said, I've heard me say over and over again, if you do control TSS, including the gross pollutants, the sand and the clay and the silt and the trash and debris, but mostly the suspended solids, you're going to be doing a very good job on nutrients as well, with nutrients being the chemicals as well, nutrients being the only exception, because they do tend to mobilize and get into this material that can float through these BMPs unless you're getting them out. Looking at the filter, this was our filter fabric in the same test. The filter fabric was coconut fiber filter. It's 3/4 inches thick. It's very difficult to get a leaf through it or a piece of pine straw. So that tends to gather on the filter. That also provides additional organic sites. But going from the bottom up again, looking at the numbers, it might be interesting to compare the clean fabric, remembering it being coconut fiber. It had phosphorus in it to begin with, 77 milligrams per kilogram. It gathered more while it was in the device, went from 77 to 477. It had nitrogen to begin with, of course, the bulk of which was TKN. It went from 160 to 1700. But going over to what we saw in the used filter, we've got about the total nitrogen, if you look at the 1767, was about 20 times as about 20 times more than the nitrates and nitrites. And total P, I say here it was 1/2 the nitrogen. It's actually more like 1/4 of the nitrogen. I have to fix that slide up. But again, total TKN and total nitrogen being about the same. You can also see that through these organics being trapped on the filter, if you look up above TKN and look at the zinc, there was a tremendous amount of zinc that was attracted to these organics. It certainly wasn't attracted to the concrete or the aluminum that we have in our device. Not enough silver in there to mine, but looking up to the lead is pretty low today based on us using unleaded gas in comparison to the zinc, but there was a significant amount of lead removed on this filter. Copper, chromium. If I were a better chemist, it'd be interesting to look at the mercury and the other materials that were not moved so effectively and try to get, first of all, they had a low concentration, and that's easy to understand, but there were worse percentages of those too, and it would be interesting to find out how organics relate poorly to arsenic and mercury and some other things that we might want to control. This could have some design implications for other materials I'd want to add to a filtering system inside of a BMP. This picture was, again, out of that report, Clean Water Management Trust Fund report. Every 90 days, we removed about 400 pounds of vegetative material. Most of it was in the trash basket. Some of it was in the sediments. Some of it was on the screen. That will tell you that a trash basket with a 1/4 inch mesh is not 100% effective at getting trash out of water, and of course, you wouldn't expect it to be. But at 2.5% of nitrogen and 25% for phosphorus, That's an additional 10 pounds of nitrogen and pound of phosphorus removed every 90 days from this particular catchment. So nutrients, it turns out, are pretty easy to control if you take the time to control them. Placing them in a big pond and deciding they're going to go away on their own is certainly not a strategy for controlling them. And as we go forward, we're going to see more and more restraints on the discharge of phosphorus and nitrogen and other nutrients into our waterways. And so as you're thinking about how to look at your next generation of BMPs or what you need to do now to retrofit, first of all, total suspended solids is important. The analysis of the sediment shows how important it is. You have to remove those solids if you're going to remove what's attached to them. Bypassing high flows will miss gross materials. They carry the bulk of nutrients. This is the #1 failure of most manufactured BMPs, is they quit too early. Now that doesn't mean they can't be supplemented with something that will catch the gross materials. In fact, quite often they are. But that bypassing of high flows also pertains to constructed wetlands and infiltration, all sorts of other things that you're allowed to bypass over the water quality flow, so you do. If you get unusually high levels of phosphorus and nutrients in your streams and lakes, you may want to take another look at that. Don't have to enlarge your forebay to 10 times the size it is now. You could simply put in a BMP that's good for trash, debris, and organics. Remember that organics are much lighter than sediments, and in general you're not going to settle them out, and that floating them in anything, whether it's a sump of a BMP or a pond or a forebay, is really not a great strategy. They're going to need to be screened and filtered out if you're going to have success. And the #1 takeaway I want people to remember today is there aren't any pollutant gnomes that come down to your ponds or your BMPs at night, swales included, and remove the nutrients. They have to be removed. A lot of folks point to the success that Florida's had in some of the roadway swales, and they don't realize that these swales are cleaned, removed, resodded, the ones that are maintained like they should be, because it's the only way to get the pollutants out. There's no chemical magic that happens other than maybe metals being taken up into organics and getting placed into the food chain that happens in these things. So at Crystal Stream, we believe you should remove things, take them out, put them away, and not doom them to being placed in water. So if we got questions, I'll be glad to take them. Jeff, you can have this back. So.
All right. Thanks, John. At this time, we'll open up the floor for questions. In the meantime, please make sure you visit crystalstream.com /free webinars and take a look at the upcoming balance of webinars for the rest of the year. Some of the topics to be covered. It's time to flush the first flush. Why design around what you can't catch in a separator? Another one will be a field study review. So once again, that's cstwebinar.com or crystalstream.com /free webinars. If you need a certificate of attendance, please feel free to email jbenty at crystalstream.com and we'll get that taken care of for you. If nobody has any other questions, at